Yeah, so this, that's called the adjoint, are these two operations, both of those operations. So you transpose it, complex conjugate it.
So that means if you have a matrix, in order to get the dagger of it, you have to transpose the complex conjugate, and that equals it.
So let me start out. So here's what I want to show you, is that for this to represent an observable, and the energy is observable, it has to be Hermitian. But now let me talk about where these parts come from. All right, and I forgot, this was a big part of what I didn't do. All right, and I have to show you. So where does H come from? All right, so
That's
we
not
got,
Planck's constant.
what's that?
That's not Planck's constant, right?
No, right now it's just a constant. But let me tell you, so now we gotta spend a little bit more time. So this is a side note away from this problem. And so I'm gonna try to do it all over here. All right? And this is an important part. So where does H come from? Where does H come from? Because I think that's ultimately what you're worried about here, Mike. All right? So here we go. Okay. So this is out of Townsend. This is a nice argument out of Townsend. Okay, and so what I'm going to do is I'm going to make this general. Remember we talked about yesterday that when a matrix operates on a ket, that it's in general a rotation, but some of those rotations are no rotations, they're just an elongation. And the special case of this is an eigenvector, right? Right? This is a special. This is a special case of this.
Right, where it doesn't rotate at all.
That's right, it stretches it, and that's when it's called eigen. All right, but what we're going to do is we're going to start off with the most general case. Right? All right, next what I'm going to do is I'm going to say, you choose to work in the basis.
Yesterday when we did that, there was a constant in front of the next.
Right.
There's no.
So I'm keeping it general. So, this is a special case of this.
Okay.
Okay?
Is that a U?
It's a little phi, I think, a little cursive phi. It's not a U. It's kind of like an angle. I need Dino here.
I was just going to say we lost our Greek again.
Yeah, exactly. Our Greek, actually. Although I'm a little bit Greek, actually. Doesn't help me. All right? Okay, so now what I'm going to do is I'm going to choose, how do you spell choose? One O or two O's?
Two.
I knew that. Oh, look at this. That is geeky. Right? I just thought of it. That's terrible. Alright? Choose to work in a basis, alright? Now, let's choose to work in a good basis. Alright? And for example, in Townsend, he decides to work in what essentially is like, maybe I'll do it this way. Let's work in a basis I hat and j hat. All right, just to connect to our vector space, like a two-dimensional space, I hat and j hat. Right? Everybody okay? Those are the basis vectors in some two-dimensional space.
Right.
Okay, so if we're in this basis, what is the projection operator equal? So Jeremy, this is what you missed. How do you make the projection operator in a given basis? You remember it's that funky object? It's the ket times the bra?
Yeah.
Yeah.
So it's
Okay. And then you sum over the basis that you're in? Right?
Right.
So would this be something like this?
So
This would be
I
like
for
I,
Yeah.
sorry, a ket, right?
You get a ket of I.
You do the
times
sum
the bra
first.
of I.
No, the bra.
You're not gonna write the sum first?
Hold on one second.
Ket. The ket of I
It's the ket I times the
bra
bra I
plus.
plus the ket
Ket
j times the bra j.
And those are commutative, right? So the way you multiply them first or last
Yeah,
changes.
they're not though, alright? They're not commutations.
So I can have, it doesn't matter that ket comes before bra, so ket.
So this is a funky object, Jeremy, that, we did it a lot in the notes, alright? So take a look at the notes and ask me a particular question, okay?
Okay.
Alright?
Projection operator.
But here's the scoop, guys. Remember, it's just like a 1. And what did it do? When it operated on something, it just expanded that thing
Right.
in the particular basis you're in.
Right, it broke it down from F to F of X.
Okay, so here's what I'm going to do. Check it out. I'm going to go H, you ready? Then 1 psi equals 1. And then times B. Is that allowed?
Sure.
Yes.
Why not?
Multiply both sides, right?
Yeah, why? Well, I don't even have to do it to both sides. I could do it to just one side. Right? Because it's just multiplying. So now you see why I call it my funky 1? Are you always free to multiply things by 1 anywhere you want?
Yeah.
So that's why I call it my funky 1. You multiply it by 1. Alright, so you're free to do it wherever it makes sense and makes your life easy. Alright, so here's what it's going to look like, alright? So let's now put it in. You ready? It's going to be H times I plus J, alright, times this thing equals I, J, plus, I. By the way, this is really a preview of next semester, okay? Because this is kind of how the Townsend book really goes to town.
I wouldn't really use this for a sales pitch.
Okay. All right. But you know, at some level, there's no functions or anything like that, so.
You like the Townsend book, huh?
Yeah, Townsend book is great, I think. Okay, so let's see if I can make sense
We
of
have
this.
the Hamiltonian times psi in the I plus psi in the J.
Yeah, so this becomes H, I, psi, plus, well, actually, I don't want to do it like that. I just want to leave it like that. We can multiply it out,
No.
okay? Okay, so, now recall, in sum of the forces equals MA, recall, sum of the forces equals MA, right? You've seen that before.
Yeah.
How many, this breaks up, it's a vector equation, right? So how many equations does it break into? Like if it's two-dimensional.
Two.
It's the x part and the y part, the sum of the forces in the x and the sum of forces in the y. So if I do this, if I went I dot this thing, what would I get? And if I went j dot this thing, what would I get?
Yeah.
Well, you get f
That would
of
be
x, and when you
I
get
F
f
of
of
one.
x, which equals ma sub x.
This would be sum of the forces in the x equals mass times acceleration in the x. And over here, this would be sum of the forces in the y equals mass times acceleration in the y.
Right.
Okay? Okay, so I have essentially this vector equation, right?
Yeah.
And it's in a given basis set. And that basis set has two bases, right? So what do you think I want to do with this then?
You have Hamiltonian psi I plus Hamiltonian psi J.
Okay, so I want to form the inner product of this whole mess with I hat,
Then with J.
just like I do down here. And then I want to form the inner product of this whole mess with J, so that I can get the two components. Okay? So I'm going to do it under here, and then when I'm all done, I want to leave this and I'm going to erase everything. I erase all this stuff. So everybody see what I'm going to do? So I'm going to now do, you ready? I'm going to do it, and it's a little bit messy. So I want to form an inner product, right? So how am I going to form the inner product here? I'm going to multiply both sides by the, I need an I, what is it, the bra or the cat?
Bra.
I'm going to do the bra, all right? So I'm going to do, the bra. So here I go. I'm going to do I times this whole thing. Okay, so this is going to get messy, all right, guys, but it's nothing hard.
And the J.
This is an abstraction, okay? The Hamiltonian does something to I hat. Remember we did that yesterday? Maybe it rotates it. So maybe it makes it like this. All right?
That lit is left.
So I'll call it I prime. All right? The next, so this forms I prime, but then what you do is you go I times I prime,
Right.
which is the dot product of I with I prime, which finds out how much of I prime is now in the x direction.
How much is left in that?
Right.
Yeah. So the Hamiltonian and matrix representation is really acting on the basis set. It's saying, what does the Hamiltonian do to the basis set? And then it's finding out how much of it has changed really.
Have you increased or decreased your amount in that direction, and then,
Yeah.
which is why if it's an eigen, it just changes magnitude in both.
Yeah,
Because
let's do a cool example, all right? Let's see if this will work. Let's say that's life, right? That's why you do physics. Right? To bang your head against the wall. Only to go backwards.
You know what's funny though? You think you're starting over to get this class, and then you get all this new stuff. It's like tricks just keep coming.
Okay, but that's why I'm trying to present it this way. I mean, I'm doing this, but in an abstract way. So if you can hold on to this is what I'm doing, you're doing great.
Yeah.
It helps you to visualize it. So
Yeah, it's an abstraction. But if you keep this picture, you're doing great, right? That gives you your guide.
now we've got
First of all, there are eigenfunctions of the Hamiltonian for the two eigenvalues. Right? Okay, but now here's the big step. In terms of this picture over here, remember that we were doing before? And we solved the differential equation?
Yeah.
So everybody take a look at this. When we solve the differential equation version over here, and we solve for these psi n's, were we not solving for the eigenvalues?
Yep.
Weren't those eigenfunctions that we were solving for? And these were our good basis set. And they essentially were a good basis set for our original Hamiltonian. Right? So what are these things over here?
the basis sets.
Those are our psi n's that we had over there. So we just solved the differential equation in terms of matrices.
Those are the eigenbasis for,
The Hamiltonian with the eigenvalues e plus and e minus.
One of those crazy formula numbers